Well, hi everybody. The sun is shining, and that means it's another webinar for Eckersley Callahan. It's all going really well so far. We apologise hugely for last week's problems. It was brilliant. Loads of people then joined us afterwards, so hopefully you've all managed to kind of see it if you want to. If you missed it because you weren't sure what was going on, we're really sorry. But the great thing is you can see it again. It has been uploaded to our website. Check out the news section of our website. Where you'll be able to find all of the other ones that have been there before and the sign up for the next couple. And we have the next one coming up, and that's Sustainable Structural Engineering, and Toby will be giving that one. So check out that one next week. Joining us this week, we've got Sam Gregson and Ben Lewis. So Sam's our kind of digital design specialist, and Ben's an associate director in the structures department. So they're going to be talking about the digital design in the developing nature of engineering processes. I'll be talking to them afterwards about getting a more easy title to read, but never mind. So a little bit of housekeeping. As you can see in the corner of your screen, there's a chat box. We've left that on as a public chat box. So say hello, send any questions in that you want to talk about. Have a nice little talk on that one. Ben and Sam will be answering questions at the end of the presentation. So, yeah, I think that all that's left to do now is to say, hand you over to Ben and Sam. Thanks very much, guys.
Great. Thanks, Kat. So, yeah, as Kat says, our webinar today is digital design in the developing nature of engineering process. So maybe firstly, what is digital design? Some people might use the term computational design, others algorithmic design, and I'm sure there's quite a few other terms commonly used out there. But for us, when we're referring to digital design, it's about the use of computer power to generate design options, be able to evaluate those options and explore a far broader kind of design space than would be humanly possible without the computer. I mean, it also encompasses lots of other aspects. For instance, how we push data from one software to the next, and finally on to fabrication and construction. Whilst there's a lot of talk in our industry about the subject, and a lot of it revolves around curvy type buildings and so-called complex geometry, so these tools and techniques can offer significant benefits to all kinds of projects, optimizing the design, reducing material consumption, reducing embodied carbon, and ultimately producing better buildings faster and maybe even cheaper. One last thing to note: digital design isn't a software. It's a concept. It's a way of working. It's a way of thinking, even. So, considering for a moment the engineering process. So the engineer's toolkit, pencil, notebook, ruler, calculator. For many years, the engineering process was largely a linear affair. The engineer received a set of drawings, did some calculations, and following this produced, a set of drawings, often with columns bigger than the architect would have liked. The advent of the computer, the PC, I don't think really changed this process too much. I mean, the calculator was replaced with Excel or another analysis program, and the pen and paper with AutoCAD. So more recently, a number of 3D modeling programs have exploded onto the market. Rhinoceros and Revit being the current market leaders. Both of these softwares have their own parametric plugins, Grasshopper and Dynamo respectively. And there's an ever-expanding ecosystem of associated plugins that takes on tasks like solar analysis, structural analysis, optimization, form finding, and interoperability. So this digital toolbox offers us the opportunity to work smarter, to collaborate more. The process is becoming more informal, blurring in some respects the roles of the engineer and the architect and other members of the team. So these are very exciting times. So the following introduces three themes. So geometry manipulation, optimization, and interoperability. Sam and I will discuss a few quick case studies under each of these headings to illustrate how digital design tools and methods are changing the way we do things. And then following this, we'll talk briefly about the approach to digital design at Eckersley O'Callaghan, and then close with a bit of speculation on the future. So geometry manipulation. I mean, almost anything is buildable in my experience if you have enough money. But most projects have a strict budget, and clients want to know that they're getting value for money. Here we look at a few projects where a number of small changes to the geometry and maybe a deeper understanding of the fabrication process, combined with our digital design skills, have added real value, reducing cost, simplifying the construction, and maybe even making the unbuildable buildable. So this was the project that came to us. It's a canopy, approximately 50 meters across, and clad with over 1,600 unique metal panels. Whilst the surface geometry is spherical, so therefore seemingly relatively rational, the panelization was based on a rotating circle going across that surface. Therefore, each panel had a slight deviation. So the resulting deviation in the panels shown here with all the panels stacked on top of each other on the left-hand side. Whilst the cladding system was an open jointed rain screen, so could accommodate some geometrical tolerance, having a joint which could be over 60 millimeters was not really an option. Also, the client wasn't keen on having a puzzle of over 1,600 individual panels. So, not wanting to completely unpick the design, we decided to adopt a different approach. So we developed a script that could analyze the panels and, based on their geometry, group them into sets of similar panels. Therefore, all of the panels in each group could then be replaced by the average panel, minimizing the number of unique panels and also the gap between them. The script used a k-mean clustering algorithm, a type of unsupervised learning algorithm, which is used for a variety of applications, from analyzing consumer markets to even astronomy. So we ran the script, increasing the number of groups from 2 up to 36, analyzing the resulting deviations, both the maximum deviation and the average, also the number of panels in each group and a few other characteristics. So this graph illustrates the results, the top curve being the maximum deviation, and the lower curve being the average deviation, the number of groups on the horizontal axis and the deviation in millimeters along the vertical axis. So for two groups, the maximum deviation was around 11 millimeters, with the average being around 4 millimeters. Considering the manufacturing and erection tolerances might be plus or minus 5 millimeters, and a desire for the minimum gap to be approximately 10 millimeters, in reality, the gap between panels could have been up to 40 millimeters if you only had two groups, therefore quite large and and undesirable. The opposite end of the spectrum, looking at 36 groups, you get an average deviation of still somewhere around 3 millimeters, but the maximum deviation reduced from 11 to 5 millimeters. Although 36 groups is quite a high number of different panel types. So what we found from analyzing the data is that with 8 groups, the deviation was only slightly greater than with 36 groups, and therefore it was considered the optimal number of panels. So this exercise dramatically reduced the complexity of the project and the cost, but with only a very small effect on the architecture.
Okay, so I'm going to talk about a different project, also in the topic of geometry manipulation. So Ben's just spoken about a previous example where we've shown that we can add value by simplifying things, making things more cost effective and improving logistics on site. But for a kind of freeform glass facade project like this, sometimes it's a question of is it even feasible? One, can we create the panels to the desired geometric intent? And if we can, does the manufacturing process that's involved in creating that geometry, is that compatible with the coatings that can be applied and the performance that's required of the facade? So it's a very complicated topic, and it really requires a good understanding of the fabrication processes, which is something we have a lot of knowledge of. So here you'll see our periodic table of glass fabrication methods, and we use this to kind of demonstrate the different processes to clients and collaborators, and show how different processes interact with each other and what's involved. So I don't expect you to be able to read all of that, but just understand that there's a wide variety of processes that glass goes through, and it can be quite overwhelming and complicated. And the different processes impact cost, the geometric kind of freedom that you have, the strength of the glass, and the coatings and the decorations that you can apply to the glass as well. Which impacts the performance, solar or insulative performance of the glass as well. And they all interact with each other in very complicated ways. And I'll just give you kind of 2 examples to demonstrate this. So here we have an image of a piece of glass being gravity slumped on a custom mold. So in this case, the glass is heated in an oven to softening point, and the glass under its gravitational self-weight kind of slumps into the desired geometry. The great thing about this is that you can achieve all sorts of complicated freeform geometries, giving lots of freedom and a really nice surface finish as well. But some of the drawbacks are the cost. For every unique piece of geometry, you need a unique mold, and the additional process of heating the glass adds further cost as well. And then there's also the fact that for this method, you basically have to compromise and choose between either the strength of your glass or coatings that can be achieved. So you're very limited on the coatings and therefore the performance using this method. On the other hand, to get a bit of curvy glass, which is all the rage, there's this method here, which is tempered bending. So here we've got a temper furnace, and the machine, you plug in the radius that you want, and the machine will bend it to the desired radius, which is great because you can get all sorts of different radiuses. The the first panel can be 2 meters, and then the next one 2.5, and there's very minimal cost implications for that. You get strong glass, and you get all the coatings you could wish for. The issue with this method is that it's just cylindrical, not S-shaped, not conical, just basic cylindrical forms. So on this project here, we've developed a script whereby we get the architectural geometry, we run the script, and it gives us initial kind of feasibility idea of the different panels. So for each panel, it will tell us, can this panel be flat? If so, that's great. That gives us maximum flexibility. If it can't be flat, can it maybe be flat and then cold bent inside? And that's the process of bringing a flat panel on inside and then kind of gently pushing it into the desired form inside a frame, for example. If not, can it be temper bent into a cylinder, like I showed, or cylindrically temper bent and then pushed into a frame? And if none of those work, then the kind of last option is slumped, which is then the most restrictive in terms of coatings, but the most geometrically free. So behind the scenes of this script, we've got kind of 2 really important processes or analyses that are carried out. The first one's illustrated by the top image on the screen, which is cylinder fitting. So for each panel, we try and find the best fit cylinder for that panel, the cylinder that best approximates the geometry. And we have a custom script which optimizes the cylinder, iteratively kind of tweaking the cylinder and finding the best match, so that the difference between the panel and the cylinder are minimized. And the second important process that runs in this script is the cold bending analysis. And so in this, what really determines whether a panel can be cold bent or not is the stresses that are produced from pushing a panel in place. You can imagine that you'll get some high stresses if you push it too much. So that gives you an idea of the kind of different processes that run in the background, and we can reuse this script on multiple projects, which is part of the benefits of writing scripts like this. Oh. Yeah, and my final point that I had on this was that this is what I've spoken about so far is purely an analysis script. We have a fixed geometry, and we analyze what are the kind of feasibility implications of this geometry. If we wanted to push that further, we've developed some tools which kind of optimize the geometry, kind of perturbing slightly the architectural geometry to try and better the feasibility or the required processes of those panels. Which kind of leads us to our next topic of the 3 that we're going to discuss, which is optimization. So optimization is quite a broad term and covers quite a lot, but in essence, it's basically trying to reach a target or an objective. That might be maximizing something, or in terms of minimizing something. And an obvious example in the case of structural engineering is minimizing weight of a structure. You might have multiple objectives, so you might want to throw in performance measurements in there as well, and there's often constraints as well, whether that's stress-driven constraints or deflection constraints. In optimization, there's lots of different techniques as well. So there's your general algorithms, which are kind of black box algorithms. They don't really know anything about the specific problem you're trying to solve, but they tweak the input parameters until they kind of find a way to minimize the objective or maximize the objective that you're looking for. And then there's kind of more problem specific algorithms, like automated beam sizing or topology optimization, which the image here kind of shows an example of. Before I move on to an example, I think it's important to stress that a really important thing to think about is what exactly are we optimizing? Why are we optimizing? And again, that goes back to understanding the specifics of the problem, the constructability. There's no point, for example, in making every beam size exactly the same length if the contractor's perfectly happy at just having an automated machine that cuts thousands of different lengths. So you really got to be aware of the impact of what you're trying to do. Next slide. Okay, so here's an example of topology optimization. This was a project where we had a steel grid shell with glass infill panels. So we got this dome structure, and in the early design phases, we wanted to use topology optimization to kind of explore the possible solutions and arrangement of steelwork. I'd like to kind of emphasize that the solutions of the topology optimization aren't necessarily to be taken literally, and really this just kind of helps us explore solutions and also kind of understand the problem and the structural behavior, what the structure kind of wants to do. So to explain a little bit about what topology optimization is, it's an iterative process, as you can see on the top there. So we start off with a mesh. Each mesh element has a different density, and then we analyze it to a given load case, and the elements which have high stresses and strains, they're obviously very important to the structure. So we add more density. The ones with low stresses and strains, we take away density. And then that's changed the structural behavior. So we analyze again and we iterate and we iterate. And you can see kind of snapshots of this process here until we converge on something. And in this case, it's interesting to kind of look at, well, what is the solution here, and can we learn something from this? So you can see that at the top, you've got a kind of grillage arrangement because it's quite flat. Then as you move down, you see that you're kind of getting columns forming. And then at the bottom, because it's bulging inwards, you've got these tie beams. So it helps to kind of understand what's happening, as well as provide some ideas.
Right, so this was quite a monster of a project that we worked on recently, a building that's almost 2 kilometers long with a roof area of something like 400,000 square meters. So designing a structure like this takes months, but this was a competition, so we didn't have that much time, and we needed to convince the client if they wanted a sustainable airport, a timber roof structure should be their only real choice. But how do you design over 10,000 beams in an afternoon and calculate the volume of carbon you could sequester from the atmosphere compared to the steel alternative? The answer was developing a simple optimization routine, so which, whilst wouldn't provide you the true optimized design, got you pretty close, 95% there, but with a fraction of the time. So another key aspect of this was developing a workflow which undertook the three-dimensional modeling, the structural analysis, and the optimization all in one parametric model. This enabling us to make quick adjustments, move column locations on the fly, and get almost instant feedback on structural depth, cost, carbon, and lots of other metrics. Unfortunately, this project didn't go forward for us, but we're continuing to develop the digital design workflow, which made it happen. and hopefully we'll use it again on another project. So interoperability, how data flows from one software to another is crucial to the effective working. There isn't one platform which does it all, I think, as we all know. Also, just because there isn't an option to export your Rhino model to Revit or whichever software you're using, that doesn't mean it's not possible. I mean, even when it is possible, it might not work for your geometry, or the data that you can translate might be limited. Having a deeper understanding of your tools is key, and is something that we promote. If there isn't a component in Grasshopper, code one yourself. If there isn't an option to import your model into Revit, or develop a bespoke workflow to make it happen. So I think the next few slides kind of illustrate some examples of this. So this is a project we worked on a year or so ago, and illustrates about how a deeper understanding of your tools can offer significant productivity benefits. Here we've got a freeform roof structure with over 600 unique cladding panels and over 650 unique tapered LVL beams supporting them. The model was generated in Rhino by the architect, but the project required that we deliver a full Revit BIM model. As I'm sure a lot of you know, Revit can be a little difficult, to say the least, with some more complex geometry, and there's no simple export-import from Rhino to Revit, well, at the time anyway. So the answer was to understand fundamentally what Revit needed to draw all of these panels. And this was simply 3 corner points of each of the panels, you know, but how do we get this information and how do we get it into Revit? So the actual solution required only 2 very short scripts, one in Grasshopper to export a list of corner points to Excel, and another one in Dynamo to import that data and generate the panels with a smart adaptive component. Therefore meaning that these 600 unique panels and their associated subframing could all be modeled in less than 2 minutes.
That's me. Okay, so another example of interoperability. There's a huge array of examples that we could have shown. I think I use interoperability for almost every project, because that's the way I like to develop my analysis models, through tools like Grasshopper, for example. But this project here is Steve Jobs Theatre, and specifically I'll be talking about the glass elevator, which you can see on the right there, that's inside. The elevator takes you from ground floor down to the lower level. You'll see that the entrance is on the back side, but the exit on the lower level is at the front here. You'll also, if you look carefully, you'll notice that the rails inside are helical. So what happens is when the lift moves down, it also twists to enable you to get in one side and exit on the other side. So it's a quite interesting project. So, I mean, this is quite an old project now. We started working on this in 2015, I believe. As Ben kind of mentioned earlier, it's really good to be kind of flexible and be able to kind of code your own tools. So there is no link between Grasshopper and Strand. Strand 7 is our kind of preferred analysis software, at least in the GLASS team, because it allows us to model these kind of structures. And what's the way we like to model these structures is we like to get into a lot of detail in the connections. So here in this example, we have bolted connections. We like to, in the glass, we like to model the hole in the glass, the bolt, the bushings, the plates, to make sure that we get an accurate global behavior, but also are able to analyze the stresses precisely in the glass and know whether the holes are too close to the edge or need moving further away or okay. So there's a lot of kind of intricacy in the modeling. And there's a lot of bolted holes in this, and if you want to move one, then it's a bit of a pain to do that once you've built up your model. So really we wanted a way to be able to change this parametrically and quite quickly. And so back then we developed this link between Grasshopper and Strand to be able to do that. And so this has become like quite a used tool across the teams, and kind of more recently, a couple of years back, we developed this further to enable us to model accurately thermal models. So here there's an example of geometrically quite a complicated penetration through a facade, and we're able to analyze the thermal bridging of this. So we've got cylindrical rebar, we've got a tapered beam, and in most commercial finite element thermal software, modeling this is quite kind of laborious. But obviously with the amazing geometric capabilities of Rhino and Grasshopper, and then our tool that we developed, we can kind of transfer that geometry across quite seamlessly. So that's an example of how we've used this to utilizing the benefits of Rhino for the geometry side. Another example is using the parametric nature of Grasshopper. So in this example, again, looking at thermal bridging, we used Grasshopper to parametrically generate hundreds of typical facade build-ups, different profiles, different insulation thicknesses, and we developed a reference database to be able to use on different projects, so we can kind of look through the database and pick the right build-up for the project without having to go and model to that level of detail every time. So that was a really useful exercise, which where we got the benefits of Strand and Grasshopper and using interoperability. So in this kind of part of the, we've spoken about the tools that we use, but how do we integrate digital design into the workplace? And I'll speak just briefly about how we do that at EOC and how we kind of, the process of thinking behind how we've organized digital design at Eckersley O'Callaghan. So there's a number of teams at Eckersley O'Callaghan. We've got glass team, we've got structures team, we've got facade team, and one kind of obvious way that you could integrate digital design is to bring in a digital design team, and there'd be benefits and drawbacks of that approach. Benefits are that you get good cohesion in the group, you get sharing and knowledge sharing in that group, but the drawbacks are that this kind of siloed digital team is not kind of able to, because it's siloed, isn't be able to keep up to date with the needs and requirements of the other teams. So instead of this centralized model, what you could do is you could go for a distributed model where you have a digital design role integrated in each of the different teams, and therefore kind of fix some of the drawbacks that we had in the centralized model. The problem with this is that then the digital design roles are kind of isolated from each other, and therefore you don't have the sharing and the motivation that you might have had before. And to kind of remedy this, you can go for a kind of hybrid model where you have your digital design roles in each of the teams, and then you bring them together to discuss and to share and talk about what's going on in digital design within each of the groups. And that's the approach that we've taken. We've got digital design roles in each of the groups, and we've got more than one representing different levels of seniority to get a good mix of people. And then beyond that, we don't want the digital design to be limited to a few people. We want to upskill the entire firm and make sure that you know, as there might be a few kind of experts who are kind of at the forefront of pushing digital design, but we want to make sure that others don't lag behind. And we want to make sure that we upskill everyone else. So we share within each of the team our knowledge, and we make sure that we teach through tutorials and seminars, and create these cyborgs in each of these teams that you see on the screen. So that's how we've approached integrating digital design. It'd be interesting to hear on the chat how maybe you've approached it in your companies. Oh, did I skip a slide? Okay, the future. So now we'll speculate on the future and what's to come. Maybe focusing on the near future. There's kind of three little subtopics that I'll run quickly through. So the first topic is goes by kind of many different names. It's machine learning, artificial intelligence, and data science. And these are kind of buzzwords at the moment, rightly or wrongly. Kind of recently, everyone got quite excited with this computer that called AlphaGo, or this algorithm that was the first algorithm to beat a grandmaster at Go, similar to the chess example that was like a decade ago, I believe. And it used deep learning to do that. Another example which catches the attention in the media was this algorithm which could tell the difference between a picture of a dog or a picture of a cat. And the way that these kind of algorithms work is you feed them a load of data, and they pick up patterns and are able to learn from that data, so that when you give it new data, it can understand it because it's learned from those patterns. And it's a little bit more complicated than that, but we don't have time to go into that. What I found recently was a paper which actually used deep learning to predict finite element analysis. Now, in this case, it came from the biology realm, which is a little bit not too close to structural buildings, but they used the aorta, the valve going into the heart, and different people's hearts have different shapes, and they used deep learning to very accurately, in a matter of seconds, produce finite element results. And I think this is kind of maybe where the strengths are, that we can utilize the data we have, not because we can't carry out finite element analyses. We have all the tools, but we can speed it up, and this will be extra beneficial in the early design stages, where we want quick solutions. We want to test things. We want to generate a number of options and see what the pros and cons are. And we don't have time to wait hours for a result to come back. So I think these kind of surrogate models is maybe where this realm is kind of heading in our industry. One of the issues is that we don't necessarily have the data. We've got lots of models maybe, but they're not kind of organized, and I think that's one thing that we're going to have to combat. and you need a lot of data for these to be successful. The next topic is augmented reality, virtual reality. I see a lot of pictures of people in goggles in architectural offices, but basically it's how we communicate with collaborators and clients. And I think there's benefits to us and there's benefits to the clients, and I think this is something we're already seeing. So there's the benefits to us is that we're doing a lot of good work behind the scenes with these parametric models, but we're not really necessarily showing them off. So I think basically revolutionizing the engineering sketch and making them more interactive so that the client or the collaborator can kind of play about with sliders and see how it affects his or her design. The power to the client, I think, is a really powerful thing that we'll see a lot more of. So digital design tools aren't just about the process of developing but a solution, but it's how we communicate that to others as well. And here are just kind of some of the tools that are available. So there's game engines and different kind of coding solutions and VR and AR as I mentioned earlier. And then the last thing that I think we're looking at that will affect the industry are the advances that happen from a manufacturing point of view. We've already spoken a number of times about how we have to be on top of how things are manufactured to know, is this feasible? What are we optimizing? And that's going to change as well. So there's going to be advances in materials and manufacturing. So there's, everything's being kind of more automated and roboticized, if that's a word, and that'll have an impact. There's kind of hot arc cutting for concrete formwork, and maybe we need to understand the processes and how the robots move to be able to do that. One example, another thing is 3D printing. It'll be interesting to see whether this really takes off. Maybe it will, maybe it won't, but I think technology is going to change and something's going to change, and we need to understand. And this serves as an interesting example here. So in this case, this is 3D printed concrete. And the concrete is kind of laid layer by layer. And what's important in this case is to, because it cures very quickly, but it's not instant. So there are limitations in the angles that you can layer these up. And it's limitations like that feed back into us, and there's a continual kind of feedback loop between us as designers and engineers and the people making it. And I think maybe we'll see a kind of closer relationship between the two. And that's it. That's our presentation. So thank you very much, everyone, for listening and sticking around.
Thanks.
And we'd be happy to take questions.
Yeah, brilliant. We're taking some questions now. I think we've got some kind of down at the bottom. There were some projects which came up earlier in the presentation, which some people were asking some questions about which projects were they. So in case you missed them, one of them was Spurbank, and that was the one with kind of the beautiful glass geometry, and that's with Zaha Hadid, and that's a techno park in Russia, very appropriate. Then there was obviously the Steve Jobs Theatre, that's in California on their park, and that's with Foster and Partners. And then LOM, I think Ben was talking about LOM with the beautiful timber geometry for the roof, and that's the Trinium Media Tech for digital design with Jacob McFarlane. So check those out if you want to see more on our website. So, but going over to the questions, I think one from Farah has been, how do you run accuracy checks on the analysis that's being done using the digital toolkit?
I mean, in a similar manner than you would using any kind of analysis software. I mean, you still get the full output of forces and loads. You check your reactions. I mean, it's just the same output. Anything to add there, Sam?
So a lot of what we're doing is using is linking two softwares together. So we're not we're not necessarily writing our own analysis packages, but we're linking packages together. So we already have like analysis packages that we know are reliable and producing the correct results, and it's just developing tools that allow them to communicate with each other.
Although some of the some of the projects that I illustrated were using Karamba inside, which is an analysis program inside Grasshopper.
Yep.
So I mean that's one kind of tool that we're trying to push further, because it really kind of benefits not having to go through the whole process of exporting and importing. It's all captured in one model. Therefore, you can have much faster turnarounds of design iterations. But as I say, it's you would check it in the same way as you would normally check structural analysis model, checking loads in equal the loads out.
On a similar sort of vein, Yanis has asked, how reliable is the linking tool between Rhino and Strand? Do you lose data in the process? I mean, does that happen kind of with other between other softwares or things like that?
I guess. I mean, in my case, I'm often building my Rhino and my Grasshopper models just to be exported into Strand. That's the whole purpose for those models. So any data that I put in, I want to be able to transfer. And so when I do that, I'm not losing any data. But I can imagine there might be circumstances where you have a model that you're feeding into Revit, or you might be feeding out into Strand, and those softwares expect different inputs. So the model that you create that might go to Revit and to your analysis software, you can't always put all of the data there. So it depends on what you're looking to do.
On that, kind of, what are the limitations do you guys see as being kind of into digital design at the moment? Are you kind of do you have kind of ideas where you could expand, or kind of where the industry could expand where it's lacking at the moment?
I mean, it's ever increasing process. I mean, as I kind of mentioned, there's so many plugins that are being developed for Rhino and other tools. I would say maybe not a limitation, but maybe where it can go is echoing what Sam said about being able to fabricate 3D print or directly from your model, from your parametric model. Then maybe that has to change the procurement process to a certain degree, but could you is that practical?
Shifting responsibilities as well, the implications in that. I think my biggest limitation is time. There's so many things that I'd like to do, but with limited time to kind of there's a lot of things that I'm kind of actively researching, but then kind of finding the time to turn that into an algorithm and to test things. I'm lucky that I have dedicated time to spend on digital design, although I do work on projects at the same time. But yeah, always more time would be great.
And I love how keen you are, Sam. It's brilliant. You mentioned 3D printing, Ben. Kind of, we've got a 3D printer in the office. How are you kind of using that within your digital design stuff? I keep seeing funky models kind of appearing all over the place and things. So how are you using that to kind of go further with the digital design?
I mean, I think it's often used to as a communication tool. So, you know, we print out our designs, and it's something that you can take to the meeting. It's something a bit more tangible. Sometimes, depending on your audience, who you're talking to, if you can hold a model in your hand rather than spin it around on the screen, people kind of understand it better. And sometimes we might print, you know, small scale models of the whole buildings, but I know Sam and his team often print you know, connection details, so you can really understand how something would go together, which is you know, invaluable, especially with some of the complex glass connections that Sam does.
Yeah. You kind of.
I'd add that it does add something to have something physical in your hand rather than just a render on a screen. We printed something out recently, just to kind of illustrate the project that we were working on, and then we showed it to the architects, and they were like, "God, is that really that big? We didn't realize it didn't look that big on the. Maybe we need to reduce that." So, you know, it added something in that.
Yeah, very much so.
But yeah, definitely. Connections are really valuable as well, as Ben mentioned, because the way that things go together can be often quite complicated, and showing that through a Rhino model is not the same as actually having a little bolt that you can kind of screw in and watch and build yourself.
Yeah, well, I suppose as kind of as construction and as the geometries become more complicated, you know, the kind of the ways in which you build it kind of have to follow, but it still comes down to, can you get a little screwdriver in to kind of, can you get a hand kind of in to be able to tighten things, I suppose. So it's useful from that point of view. There was a question which I was actually thinking about, but it's coming from kind of Munib, and it's saying, what advice would you give for young engineers to develop digital design skills? And I suppose, are you seeing grads coming through with the right skills, or, you know, is it something which universities aren't covering so far? Do you have to learn on the job, basically?
I don't think many universities are necessarily looking at digital design skills. There are some that kind of look a little bit into coding. I actually started my degree doing aeronautical engineering before I switched to civil engineering, and there was some coding in that. But then I got to civil engineering and there wasn't any. So I don't think they are teaching it. I don't think that's necessarily that important. I think in a decade everyone will know how to code anyway. I think they're starting to teach like 5-year-olds to code. So and I learned on the job. I think my advice would be, like, don't wait for a specific job before you dive into these tools, because these tools can be used on the most mundane jobs, and you've just got to push yourself. I remember trying to push digital design in another team in another company I worked for, and I got 2 responses which were quite interesting. I was trying to. Someone was really keen to learn, but they were like, "Well, this project's too simple. It's not really built for digital design. I'll wait for the right project to come along, something a little bit more complicated that needs these tools." And then I got another response from another person. Who said, "Yeah, I'd really like to try these tools, but I've got this project and it's just too complicated. Like, there's just too much going on. I can't use it. I'll wait for a simpler project to come along before I delve into these tools." So I think the message just get stuck in.
I can second that. I've been trying to use Grasshopper to design my bedside table that I'm going to make. So I think it could be for anything. It's a great tool. So
it's just about looking for the opportunities.
Absolutely,
yeah.
It's great fun. It's opened up a whole new world for me. So it's it's great fun.
And I'd add, like, it's the same as any tool. If you're learning how to use a piece of finite element analysis software, the first time you design a simple beam, it takes way longer than if you were to do a simple hand calc. But that doesn't mean that it's not valuable learning it. And then the first few times it will be a bit slower than by doing it by hand. But you've got to get over that kind of milestone.
Yeah, and once you do, the possibilities are endless, as you say. So, okay, so one more question. I think this is quite specific, but we'll dive into it anyway. Let's see. I saw at the beginning the logo of a Caramba, have I got that right? Caramba 3D plugin. I was wondering if you can use it in your projects, and how reliable you believe it is compared to Strand. Quite a specific question, but question nonetheless.
Okay, I'm not sure how reliable in comparison to Strand, but I mean, we've been using Caramba for about a year or so now, and we often use it as a kind of early stage analysis tool, concept tool. Although, you know, we have run some benchmarking exercise, benchmarking it against Robot, and the results seem to match pretty well. So it seems a fairly reliable piece of software in my experience.
Sam, anything to add?
Do you have any? Have you used it compared to Strand, Sam?
I haven't done much benchmarking. To be honest, I mainly use our Strand link because of the models that I'm doing and the capabilities of Strand. There's a lot more flexibility. As I showed, we can do thermal modeling of Strand. There's a lot more options for dynamics, kind of footfall analysis and that kind of thing. So I don't think it's really a question of reliability. It's a question of what the software can do and the limitations of the software. So yeah, at the end of the day, it's just matrix inversion, which you learn at school or at uni. So it's not necessarily that complicated. It's about the interfaces and that kind of thing.
I mean, one thing I'd say that I like about Caramba is you have access to all of the data, and you can visualize that data in any way you want. You're not constrained like you are in Robot to only see certain types of diagrams. Using Caramba in Grasshopper, you can visualize it however you want.
Absolutely. Well, I think we've just had one more question. Shall I go for it? Do we have time? Let's go for it. Have you been able to account for the embodied carbon in the offcuts of the cylindrical formed glass elements? Another specific one, but a good one for sustainability in terms of digital design and the like.
Could you repeat the question?
Yep. So have you been able to account for the embodied carbon in the offcuts of cylindrical formed glass elements?
No, not specifically, but I mean, embodied carbon is a huge topic, and it's only ever going to become increasingly more important for clients and collaborators. A lot of it is dependent when it comes to glasses. A lot of it is dependent on more the process. So slumped glass is more energy intensive compared to tempered glass, for example. But it also it's hugely complex, and we're gathering data from fabricators. At the moment, it's one of our kind of research topics to understand exactly where the embodied carbon is really coming from. And there's so many variables, transport, for example, you know, whether we're getting the glass from China or whether it's coming from Germany, and where the project is. So there's a lot of things to think about, and we're actively researching to kind of understand this more and learn more from the industry.
Yeah, very much so. There's a lot of work that we're doing about sustainability, and we've got a launch coming up about sustainability at some stage very soon. So watch out for that. So on that note, I will wrap it up. Don't forget, we've got 2 more coming up so far. There's another one. We might have a new series coming up very soon. So watch out for the announcement of some new ones coming up. Next week is Sustainable Structural Engineering by Toby, one of our directors for structural engineering. And the one after that is The Circular Economy of Facades by Simon Pearce, one of our associate directors. So tune in for those. As always, these are recorded and they're put up onto our website. So from tomorrow, you'll be able to see this one backup online. So if you look at the news section of our website, check that out. You can see all the back history. So you can see Damien's, Hugh's, James's, and who else missed? Ian and Graham's.
Ian and Graham.
So yeah, check those out. And I hope you have a lovely Friday for those of you who have it off in the UK. For our people around the world, very sorry, probably don't get that, but I hope things are going well for you. And hope to see you next week. Super. Thank you very much indeed, guys. Take care. Bye. Bye.
Thanks. Bye.
Thank you. Bye.